welcome back to the hyperbolic coding chamber. We are back once again. I am in deep within the Coliseum of the heaps. Okay, so I'm kind of the heap god. TLDR, I'm kind of the heap god. Not really, we're kind of deep in the heap stuff. We kind of have a function working that kind of works with the insert. We'll see how it goes. But I'm feeling like, One Piece spoilers ahead, I'm feeling like when Ace died and his fruit comes back and then Sabo picks up the fruit. The fruit is the knowledge of the heaps. And basically I'm Sabo with the fired fruit. So, the heap grind continues. That being the case, it just kind of be like that. Fortunately, we have some comments that are going to help us stall before we have to go into the death chamber. But we have a comment from a legendary human being, Wilderness, who dropped some big facts in the chat the other day. Also with a pretty cool, this is top 2 anime and it's not 2. So if you haven't seen it, you should definitely check out Hunter x Hunter. From Wilderness, make the kind of content that keeps you making content. Shall we? It doesn't get any better than that. Appreciate the comment, brother, and it is true. I think there's the more I think about it, there's definitely a discipline factor to things for certain, but I definitely do think there has to be a little bit of dopamine in there somewhere. So sometimes it feels like the slow drip of dopamine that comes out of something is just dog, and it's just not enough. So if I managed my environment and then it turned out things got better, it was easier to do those things. But I also realized there has to be a little bit of at least a slight dopamine drip to make it worth it. At least a little bit. So that being the case, maybe there's a cheat code where another cheat code is to do things with a slight dopamine drip. Maybe doing things where all the dopamine's at the end is kind of difficult. But maybe it's hard to know. It's hard to know if the people who end up making things at the end are using the slight dopamine drip cheat code, like an IV into their veins, and then at the end they get a big payoff, or if everyone's just stone colding it. Because I would be lying if I said I don't get at least a little bit of dopamine from LeetCode. I definitely feel a slight dopamine drip, but yeah. So, is discipline just another way to say that we need to become accustomed to the slow dopamine drip if it exists? There's some things that I work on where there's no IV-like drip for dopamine. So, or at least that's what I thought. It depends. Stuff is so general, but it really does depend. Because there were some things that I thought I got no IV drip from, and then I kind of managed my environment, and the sensitivity went down, and I was able to kind of pick up on that I was getting something out of it. So, it's pretty much a never-ending battle of that. That being the case, things are changing. I feel a strong pull to grind out the LeetCode and pump out a bunch of explanation videos, even though there's hundreds or tons of these videos out there already. But I don't know, teaching is pretty cool, and hopefully maybe our conceptualization of the problem helps someone else. That would be cool. But also, what else is there to be even doing? So I don't know. I've just been thinking a lot. Actually, I haven't been thinking as much recently. I've mostly just been reading. So I feel like something's coming, though, or that something is about to change. But it's hard to put my finger on why I think that is. I've been also, I guess I should also mention this, I have been managing my environment more aggressively the last 2 weeks. So I haven't been binging anything at all, whether it's anime or food. Actually, I did binge on a little bit of food, but I've been trying to manage the environment recently, and I gotta say, things have definitely been easier life-wise. So, yeah, there's something about the high and low, that frequency that just makes things difficult. When I'm during the day, if I'm rubber banding between high and low, then work becomes very difficult. Just doing anything in general comes really hard. So when I'm managing my environment, there's less rubber banding, and so it just feels a little bit more stable. So that's pretty dope, to be honest. But at the same time, when I felt like this before, when I had managed my environment, this is actually when I started LeetCode, and somehow we've kept up with it. So I'm started managing it a little more aggressively now, and I think maybe that's why I feel like something's coming, because I feel my I sometimes feel like I can feel my head slowly returning to baseline, and then I get like a push. For example, there are other things outside of LeetCode that I was struggling to do, and now I'm seeing with the management of the environment, I feel a slow burn coming. So it's been easier to do other things to kind of to add more onto the plate. So I feel like I'm only on like day 14 or day 15. So hopefully if we can keep managing the binge, I feel like we could truly unlock some potential. So that being the case, it's been incredible to see how far so little time every day has taken us. So hopefully we can unlock the rest of the DLC for our brains, and maybe we'll get something cool out of it. Or maybe nothing. I'm not sure which one's worse. So that being the case, if this is something that you're interested in, you should join the Hyperbolic Coding Chamber Discord, which is Discord dedicated to figuring out all there is to figure out about heaps. And we have nothing else to say but just to get back to it. So also shout out Wilderness. And yeah, we're still working on kth largest. We used our hour yesterday to pretty much force the insert function into existence, and we were able to force that insert function into existence, and I think it is kind of working. What remains now is to see if we can get the delete function working, which should also work in log event time, and then we can kind of keep rolling through the heap problems. But my brain is kind of sauced, I'm not going to lie. Had a very long day at work. It was very satisfying, but my brain is definitely fried. I'm feeling like the end of less yesterday's session, but at the beginning. So some of our best sessions have happened like that. So I guess we'll just show up. So we have the insert function working. We kept the history using the bottom right nodes array. If I click one, I think we added some testing to the constructor, and we're able to see that we do indeed get the values that we're looking for in the correct order, in a complete binary tree, and I think while adhering to the rules of the heap. Negative 320 is the smallest number, with its children being -1 and -3, which are also the second and third smallest numbers, followed by -1's children being 4 and 1, and the left node of -3 being 3. So that looks kind of promising. And this was split up into two sections, which was the section that pretty much allows the allows the heap to be a complete binary tree. And then I think we can just copy this whole thing. And then I'm just gonna paste it. So if I hit delete, we're not gonna pass anything, but we should get a number in return, right? And I'm pretty sure based on the problem statement, we're already safe to assume that add won't be called on an empty, get won't be called on an, add, which is the function we're actually implementing, will be called, but k will never be less than the total number the total amount of numbers in the tree will never be less than k, which is a safe assumption to make based off of the problem. So when we have this delete function here, it's unlikely that this dot root would not exist. Let's shift all this back once. And for some reason, the Vim emulation with the shifting is just kind of broken recently, and I'm not exactly certain why. But maybe that's okay. We have a const node called brmn, which is the bottom rightmost node. If we want to delete a number from the top, the number we want to delete is indefinitely going to be this dot root, right? Which we're going to want to keep a temporary node of. At the end, we don't really have to worry about anything else, since we can just say, we can just return temp.val, which would have been the number at the top. The problem is, if we have a history already created, right, let's just say our tree, we insert the numbers listed here. If we insert the numbers listed here, they should, by default of the add function, I should have called it insert. Right, so by way of the insert function, we should be safe. And let's assemble this into the correct heap. We should have 3 here, probably 4 here. No, we would have 1, and then 3, and then the children here would be 4 and 6. Right, -1 is smaller, it's the smallest out of all these numbers, right? And 1 is smaller than 4 and 6, right? And so I think we would be safe. Now the problem is, I'm pretty sure if we checked our history would look something like this: 4, 6, 3. And I think we can test this if, wow, we have so much stuff here. For some reason it's complaining about insert. Oh, I see. So we should be good now. So if we were to reach into heap after all this nonsense and just do heap, this dot heap dot bottom rightmost nodes, let's see what the history looks like. It should look like what we said it would look like. And then we have to fix this quick error up here, because val doesn't exist, right? And I'm just gonna comment out everything else here, as well as this stuff too. So it looks like we have 1. No, we have -3, 4, and 1, and 3. Right, our insert values change. So we have -3, which is good, and we should have 4, because if we imagine this into a tree, -3 is going to be at the top, -1, -3 would be 2 children below that. Then we'd have 4 and 1 under -3. So we should have -3, 4, 1, and 3. That looks good. That looks good with -3. That looks good with -3. Yeah, the bottom rightmost node should be the first node. So if I change the array, I inserted something like this. We check what's printed, we get -1 1 6 4 3. And if we check the bottom rightmost nodes, we have 1, which doesn't quite strike me as the bottom rightmost node. It looks like what they're saying is the tree they have is this. And then the history nodes that we actually have. There's too many trees here. It's hard, it's impossible to focus. -1, 1 6 4 and 3. Now the nodes are actually there in the bottom right ones were 1 6 1 6 Yeah, I also just realized if we set the right node here, then we should also do this dot bottom rightmost. Because it already has 2 children, there's no way. So we check this now. We have a parent of -1. No, we have a value of 6, which makes sense. This parent is -1, so this one actually looks like this. 6 goes right here. And 1 goes right here. We have 4 whose parent is 1. Wait, what? We have 4 whose parent is 1. 6 whose parent is -1. 3 whose parent is 1. And 6. 6, 3. So I guess it's still actually a heap. 1 is smaller than 4 and 3. Alright, so the next bottom rightmost node would be 6, which is why it's up next here. But to make sure that it's still a binary tree when we rearrange it, if we delete -1, right, the node that's supposed to go here is 3. And then it'll keep swapping its elements until it's not greater. Oh, it'll keep swapping with its smallest child. So we have 3, 1. So I think we could implement that. New root would actually be equal to this dot bottom rightmost nodes dot length -1. So the last element in there, and it's going to be the new root. So we'd actually say new root dot So we actually say new root dot parent we'd say if new root dot parent exists, and then we'd say if new root dot parent dot val equals new root dot val, then new root, oops, copy this. So that value, so we have to remove that node somehow. This is us removing that node, and now we still have access to new root. And I guess another way to do that is just to say pop. Afterwards, we can say new root dot left equals temp dot left. New root dot right is equal to temp dot right. And I guess to save us all the hassle, we can just basically just say this dot root dot val would be equal to new root dot val, and we'll technically have swapped it. So if I keep one of those, So in the actual class itself of the solution we're actually supposed to submit, I'm going to delete all this nonsense in here because it's making it hard to read. Instead of calling print here, I'm going to call this.heap.delete. And we should get -1. So we do get negative. Yeah, so with this, after node deletion, we see see 3 is at the top, right? It doesn't quite make sense, right? Because 3 is not less than 1. But we are getting -1, which makes sense. So now we just need to do the shuffling part. So now we just need to do the shuffling part. And the shuffling part is we need the smallest child. So we basically need to say, and I guess we already have some of this stuff here. And we also, yeah, that's true. We also want to fix the parent relationships. This dot root dot left dot parent equals new root. Actually, no, we don't have to do any of this nonsense, thankfully. We'll say while new root dot val is less than so if new root dot left exists, right, and new root dot val is less than new root dot left dot val, or right, if new root dot right exists, and it's just going to be the same thing. New root dot right, new root dot val. It's the new root. So So new root dot val, new root and new root dot val is less than new root dot right dot val. We have to do a substitute with the smallest element. So the substitution with the smallest element, we end up duplicating a lot of cases here. There's got to be a way to, let's say if new root dot left exists, actually we can do something like this. New root dot val is less than new root dot left dot val. Nah, that's just made it worse. So we'll say if here then it means new root dot left dot val is less than new root dot right dot val, which will default to positive infinity. Then we'll swap left. Otherwise, we'll swap right. I mean, I'm sure there's a better way to implement this, so I can't wait till we get to that, because our version is very ghetto. I'll say const say let new root equals this value. We'll say temp is going to be equal to dot left dot val. Yeah, this isn't gonna work. So if new root So we'll say that the swap for is going to be new root dot left dot val is less than or equal to new root dot right dot val. The swapper is going to be new root dot left. Which means that we have saved that value, so new root dot val should equal swapper dot val. And then here it means only one of them exist. So if new root dot left, then we just have to swap the values in those nodes. So say const temp equals new root dot val. Since we're saving new root dot val, we're going to overwrite it with new root dot left dot val. And then oh god, this is torture. After the shuffle, it literally doesn't change. So maybe this isn't running. So you have now you have 1, which is less than 3 and 6, and 4. I think I might be taking it from the wrong angle. If we have 3, if I remove it and there's 3 at the top, I'm looking at like, oh, 3 is greater than it should, and so it should swap. Which it does. Actually, this kind of does look right, actually. After the shuffle, we have 1, 3, 6, and 4. So let's test this. I'm going to change this dot heap to t heap, which is going to be our test heap that we've been testing this whole time. And then here we'll actually do 4 const num of nums, and we'll just do this dot heap dot insert num. And then we also need a size variable. Pretty much whenever we say this dot size minus equal 1, and then we'll say in here, while this dot heap dot size is greater than k, this dot heap dot delete. And then we'll just say, yeah, we'll just do it like that. And I think we should be good. So when we do add, we'll just do this dot heap dot insert val, and we'll say this dot heap dot size is greater than k. This dot heap dot delete, and what we return will be this dot heap dot root dot val. No way. Oh, oh man, that was bad. I forgot to comment out the logging. Oh my god. Oh my god. Okay, I am the heap god. I am the heap god. There's no way. I literally wrote that last bit thinking I'm gonna click run, this thing is literally gonna explode. But we actually got the shifting right on the first try. Yeah, 0.5x video watching is unbalanced. The time complexity diff is actually crazy. Here we have 280 milliseconds. And before that, our original accepted answer was 5 seconds. And we actually implemented a heap. This is crazy. I think we might have to take a break on the heap. Maybe this would be ideal. Maybe it's prime time to go even deeper. But yeah, our heap implementation is absolute carnage. I mean, imagine having to implement this in an interview. There's just too much going on here. Maybe there's gotta be a simpler, concise way to implement a heap. Because getting into the depth with all this logic this is really important because now we have a way of keeping track of the bottom rightmost nodes to make a tree, complete binary tree, but also the node, wait a second. I actually don't understand something. Right, to remove an element in the binary tree and also keep it a complete binary tree, we need to remove the rightmost node. It does not mean that it's the bottom rightmost node, or it means the latest node that we added, which would retain the fact that it's a binary tree. Since we're adding from top to bottom, left to right, our history gives us a history of bottom left nodes from left to right. So if we get the end of it, we're getting the node that we can remove, that we're removing from the right hand side in certain contexts, which would give us a complete binary tree that still works. So that was pretty cool. I'll be right back. 17 minutes remain. Yeah, that was incredible. That was some dopamine right there. So it don't get much better than that. So that was a heap problem. I'm pretty sure we're working on the Explore card, and it should be solved by now. While they had applications of a heap, top K. Heap sort top K. Hey, top K is what we just solved. Kth element is what we just solved. Top K problem is also solvable with a heap. And then there's also heap sort, which I guess if you included a node for the occurrences, you could do some special stuff here. Then it looks like they have some practices. They have meeting rooms, stone weight, which we just did this, and I'm gonna copy and paste our solution here for the pure dopamine of seeing that babe. So it's basically the same thing. If we were to do 15 of these problems, or how many are here, like 12 or 13, and implement a heap every time, it would be kind of nutty. So I think we'll just do one more random problem, and then tomorrow we'll see if we can implement a heap that actually makes sense. So we'll start this one, but tomorrow we'll see if we can find an implementation that's not nonsensical. So we have a string. A string is a valid parenthesis string, denoted VPS, if it meets one of the following: it is an empty string, or a single character, not maximum nesting depth of parentheses. It is an empty string, or a single character not equal to left parenthesis or right parenthesis. It can be written as AB, A concatenated with B, where A and B are both valid parenthesis strings, or it can be written as A, where A is a VPS. We can simplify the nesting depth S. You can similarly define the nesting depth S of any VPS S as follows. We can similarly define the nesting depth S of any VPS S as follows. Depth is equal to 0. Depth of C is equal to 0, where C is a string with a single character not equal. Depth of C is equal to 0, where C is a string with a single character not equal. Not equal to a single parentheses or the right one. Depth A plus B I see. So in the case where we have two nested parentheses, the depth is the max of the two. If we have parentheses and a character in the center, or another VPS in the center, the depth is 1. It seems like you could solve this with a stack, where the stack would be an array of strings which would only ever have opening parentheses within it. And then we could do for const letter of s. And then here we'll have max depth, which will be equal to negative infinity. In each iteration, max depth will be set to the math.max of max depth, or the length of the stack. At the end here, we can return stack. We can return max depth. We can't return max depth. We'll call it depth because we're gonna have a variable shadowing. And then we'll change this to depth, and then we'll say if letter is equal to an opening parenthesis, we'll say stack dot push an opening parenthesis. Similarly, else if it equals a right parenthesis, we'll do stack dot pop. I'm not exactly certain. Maybe you have to have it in a block. I'm not following what the problem is here. Line 7, a semicolon is expected. We have letter triple equals a string. Oh my god, this should be else if. That's how you know. So yeah, my brain is fried. Nice. It feels like this would be linear time as well as linear space. We'll try one more. Largest local values in a matrix. You are given an n by n integer matrix grid. Generate an integer matrix, max local. This one looks a little bit more involved. So actually, I think with today, I think it's okay. At the time, yeah, I think it's okay for us to stop here.